This video provides additional visual material for our paper, Multitask Spatial-Temporal Graph Auto-Encoder for Hand Motion Denoising. Part 1, Introduction. The importance of human hands in human-computer interaction, HCI, techniques is increasing rapidly. These are some of the challenges that arise when dealing with hand motion data in HCI applications. On the one hand, the complex articulations, self-occlusion, and self-similarity of hands make tracking and pose estimation challenging. Moreover, prolonged operation and movement disorders such as Parkinson's disease may lead to involuntary handshakes, resulting in interaction failures. Additionally, inaccurate data acquisition methods can result in noisy data. On the other hand, the user experience deteriorates when applications lag due to delays in the processing and rendering pipeline. The first challenge of inaccurate tracking and handshakes can be tackled by denoising. The second challenge of improving system response speed can be tackled by prediction. While denoising can improve the quality of hand motion data, it can cause the oversmoothing problem. On the other hand, prediction alone may generate noisy outputs by ignoring the noise in the raw data. We were motivated to address the aforementioned issues by proposing a multitask framework for hand motion denoising that integrates the prediction task into the denoising process. Part 2, Model Architecture. The framework consists of three main components: a shared motion encoder, SME, denoising, and prediction branches. Firstly, the raw motion data is input into the SME, which projects the input to a compact and versatile latent space, where both denoising and prediction branches can remove noise while maintaining temporal dynamics. A gating mechanism is implemented to prevent the latent representation from causing harm to others. In the denoising branch, the shared latent variable is passed through the denoising gating unit, DGU, and the motion denoising decoder, MDD, to obtain the noise signal, which is then used to produce the denoising result. The prediction branch adds the shared latent variable to the positional encoding, PE, after passing through the prediction gating unit, PGU. The future motion offset is determined using the motion prediction decoder, MPD, and the predicted result is obtained by adding the seed pose from the denoised branch. The PE module ensures the sequential property of the motion data as a time series, which is not modeled by the original STGCN. Overall, this multitask framework effectively denoise and predicts hand motion data, improving the accuracy and reliability. Part 3, Data Synthesis Process. The process of hand motion data synthesis involves corrupting the original hand motion data using shifting noise, shifting mask, and occlusion mask. The corrupted data is generated by scaling the original data, adding uniform random noise, and applying binary masks for occlusion. However, adding noise to each joint separately can cause joints to deviate from their original position and disregard the hinge structure of the hand, resulting in poor generalization. To address this issue, we propose an optimization process. We optimize the corrupted data by starting from a node close to the root and moving toward nodes farther away. The child nodes inherit the shift correction from their parent node and then correct themselves, which avoids generating extremely unreasonable noise and facilitates the learning of complex spatial-temporal patterns by the network. In this way, this optimization process leads to better generalization. Part 4, Denoising Results. We present a hand motion and the corresponding noisy data. And we use our proposed method to obtain the output motion. To qualitatively evaluate different methods, we use transparent shading to visually visualize the ground truth in the output video. As we can see, our denoising results almost exactly match the ground truth, indicating the effectiveness of our algorithm. Then, we show the comparative results with state-of-the-arts. We first compare our previous method, STGAE. We first compare our new multitask framework for hand motion denoising to our previous method, STGAE, which uses a spatial-temporal graph autoencoder. While STGAE achieves better results on most frames, there are some frames with large errors, particularly at the fingertips. This may be due to STGAE's focus solely on denoising, which can result in oversmoothed fingertip motions. However, by integrating the prediction task, our multitask method preserves dynamic information and addresses this issue. Our results demonstrate the effectiveness of the proposed framework. To further validate the effectiveness of our proposed multitask framework for hand motion denoising, we have also implemented two other state-of-the-art methods for qualitative comparison. From the output videos, it is evident that our method outperforms the other two methods in terms of stability and denoising effectiveness. Both of the other methods exhibit obvious jitter and some frames with large errors. In contrast, our method is relatively stable and shows fewer errors. This is because our method takes into account the complex structural constraints of the hand, resulting in better results than other methods. We show more demos. Part 5, Prediction Results. We demonstrate the prediction performance without denoising, which produces poor results with significant hand deformation. However, our multitask framework achieves good prediction results, indicating the effectiveness of multitask learning for prediction tasks. Additionally, our experiments show that the multitask framework outperforms any single task. We show more examples. Part 6, Conclusion and Future Work. In summary, we proposed a multitask framework, Multi-STGAE. The proposed method achieves better results than state-of-the-art methods. There are still some limitations to our work, such as the domain gap issue. Future research could explore incorporating unsupervised learning and collecting more real motion data to improve the generalization performance of the model. Additionally, the proposed method could be extended to other types of motion data and applied to different fields, such as robotics and virtual reality. Thanks for your watching.